Let's quickly review the four fundamental forces. You said there was gravity, mass attracts mass. We know how, but we don't know why mass attracts mass. There's the electromagnetic force. So you may notice that if I take these two markers here and bring them really close together, watch what happens. Nothing, right? But if I take these two pieces of metal and I bring them really close together, so why is it that when I bring two markers together, nothing happens, but if we bring two pieces of metal together, that happens? So what should we call that phenomenon? We got to give it a name. Should we call it Liberty Gibbets? We called it charge, right? So electromagnetic force, that there are things with opposite charges. And these opposite charges attract. So what should we call these opposite charges? Yin and yang? Black and white? Good and evil? The names they settled on were positive and negative. So opposite charges attract. We call one type of charge positive, one type of charge negative. And it's the same thing with magnetism, except we don't really say that it's got a positive side and a negative side. We say it's got a north pole and a south pole. The north pole is attracted to the south pole is attracted to the north. You bring two north poles together, they'll repel. Now, sometimes these forces work together, sometimes these forces work against each other. And that's where I was trying to show you my levitating globe, which isn't working. But gravity pulls the globe down, and then electromagnetism repels and holds the globe up. So you can overcome the force of gravity if you have a strong enough magnet. And there are actually trains that levitate on rails. They have electromagnetic rails, and the magnetism is so great that they can levitate a train. Somehow. Get the wrong magnets. There we go. You can levitate the train above the magnet, and essentially the train is hovering off the ground. And why would you do that? Because then you have no friction. No friction, the train can go faster and you use less energy. Third one was the strong nuclear force. Did we write this one up? Did we get this far?
Yeah,
This one is
So, did we define this?
no.
The strong nuclear force is a force where protons attract protons, neutrons attract protons, and protons attract neutrons. So it's another force that causes protons to attract to protons, neutrons to attract to protons, protons to attract neutrons. And we'll just list the last one, even though we're not going to spend any time talking about it. And we're really not going to spend any time talking about 1 or 2 either. When you take physics next year, you'll spend all year talking about gravity and electromagnetism. But we're going to briefly talk about the strong nuclear force in terms of radiation. But just so that we weak nuclear force causes quarks to change type. So if you go on in science and go on in nuclear chemistry, you can study that. But as far as what I'm expecting you to know and understand, John, is I want you to be able to list them. That's it. There are 4 forces in the universe: gravity, electromagnetic, strong nuclear force, weak nuclear force. That's as far as we need to go. Okay. Just as an aside, when you were doing that worksheet last night, they talked about quarks, and that, can you find a quark by itself? No, they always come in threes, right? Now, what attracts quarks to each other is this kind of this weak nuclear force. Now, they don't call it charge per se because the word charge has already been taken for electromagnetism. So what did they call it down here? They said they had color, right? Quarks really don't have color, but they had to come up with a way to explain how they attract each other. Up here they use the words positive and negative. They could have picked, like I said, yin and yang, good and evil. But down here, since those positive and negative were already taken, they decided to say that quarks have color, and that opposite colors attract. All right. Any questions so far? So we know that atoms are made up of protons, electrons, and neutrons, right? And protons go in the center. So let's do the simplest atom in the universe. Hydrogen has 1 proton. How do I know it's got 1 proton? Because the atomic number of hydrogen is 1. The number on the bottom, the atomic number. And it tells me the number of protons. Need more space. So there's 1 proton. And for right now, we're just going to deal with neutral atoms. And for neutral atoms, the number of electrons is also the same as the number of protons. So if you have 1 proton, Mark, you can have 1 electron. So the atomic number up on the periodic table are actually the blue numbers in the upper right-hand corner. So carbon has 6 protons, oxygen has 8 protons, but when you write it on a piece of paper in front of you, you put it in the lower left-hand corner, just to confuse you. So when you look on the periodic table, it's in the upper right-hand corner, but when you write it on a piece of paper, it goes on the lower left-hand corner. The number in the upper left-hand corner is the atomic mass. mass of the atom. And if you subtract these two numbers, you get the number of neutrons. So hydrogen is an atomic mass of 1, an atomic number of 1. If you subtract the two, you get 0 neutrons. So hydrogen is 1 proton, 1 electron, 1 neutron. And if I were to draw it, this is what it would look like. And that's pretty much as far as your understanding has gone, Rachel. Right? Your middle school or high school or a freshman high school teacher said electron. Use electron.
But like where is that the atomic mass?
The number of protons equals the number of electrons.
Oh.
Or actually the other way around. The number of electrons equals the number of protons. So where do we put the protons? In the nucleus. Where do the electrons go? Around it. And that's about where you left off at. So let's try doing the same thing, but for the next most complex atom, let's do helium. So Ryan, what's the atomic number of helium?
2.
You left out. Yes, 2. What's the atomic mass of helium, Brenna?
2.
The blue numbers are the atomic mass. I'm sorry. The blue numbers are the atomic numbers. The red numbers up there, Brenna, are the atomic mass.
Oh.
So I know it's confusing, but these numbers are the atomic numbers. These numbers are the atomic mass. So for helium, the atomic mass is 4. You just round to the nearest whole number. So how many protons? How many protons does helium have?
4. Counting 2.
2. So I gotta draw another proton in here, right? I have 2 protons. And I have how many electrons then, Chloe? 2. So I draw another electron in. And then you smiled at your middle school teacher or your freshman high school teacher and said, okay, that's great. And then you moved on to the next topic. But what is wrong with this model of the atom? Why do you need neutrons? I mean, it's like that person who shows the third wheel on a date and you're like, why are you here? Can't you go home? Can't you get a hint? I mean, why do we have neutrons? Think of the first 4 forces. Okay, mass attracts mass, right? So protons will attract protons, okay? Electromagnetic force. What happens with the electromagnetic force? Opposite charges attract, and what do like charges do? Repel. So why would you put the 2 positive charges right next to each other? They don't like it. They want to get away from each other. They are repelling. And so it wouldn't make sense to put the positive charges right next to each other. Why not do this? Alternate. Go electron, proton, electron, proton. And that's an atom. It'd make a lot more sense. Balance all the charges out. And unfortunately, it doesn't match up with experiment because we know there's a nucleus, we know the protons are in the center, but so we know the protons are in the center, we know there's a nucleus, but then again, how are they sticking together? And that's where the strong nuclear force comes into play. You've got the electromagnetic force saying repel. So the protons actually do want to repel. But when I put the neutrons in, the neutrons kind of act like glue. In that the strong nuclear force I'm going to abbreviate it SNF. The strong nuclear force causes neutrons to be attracted to protons, and neutrons to be attracted to neutrons, and protons to be attracted to protons. So the strong nuclear force is like a glue that keeps the nucleus bound together. So you have this tension. The protons that want to bust apart, and the neutrons that say, no, let's stick together. Let's do carbon. Right now, we're going to take the atomic mass and round it to the nearest whole number. Yeah, Jake.
How do the protons attract protons, but they also repel? Like, they repel. You know what I'm saying? Electromagnetic. says
There are two
repel.
different forces in action. Okay, so this has mass, right? And this has mass. These two things have mass. So they actually attract through gravity. But they also have like charges, so they repel. So who's going to be stronger, the gravity between these two objects or the electromagnetic repulsion? In this case, the electromagnetic repulsion, and it levitates. Okay, so you can have, things can have more than one force acting on them, and then you have to figure out which one's going to be stronger. Did you have a
So
question,
it's,
Alex?
yeah, so it's like just a matter of one force overpowering the other one?
Yeah. So if we go to carbon, now we've got 6 protons, and you don't need to draw this. Six protons, what does that do to the repulsion? It increases it, right? More positive charges, more repulsion. So then, what do you think we're going to need to do? Add more neutrons. How many neutrons should we add? Well, if we add 6, we achieve stability. Again, it's the glue. And if you look at the periodic table, you see a pattern. Protons, 6, neutrons, 6. Go to nitrogen. Protons, 7, neutrons, 7. If you go to neon, ten protons, 10 neutrons. So the more protons you have, the more protons, the more repulsion, and so you're going to need more neutrons. Now when you get really high in the periodic table, let's do, how about silver? silver, the atomic number is 47. So that means we have 47 protons. 47 positive charges crammed in the center. That's a lot of repulsion. So the higher you go up on the periodic table, you need lots and lots of more glue. So the further you go up on the periodic table, you find that you need more and more neutrons to get it to stick together. And eventually, you're going to get so high on the periodic table that no number of neutrons will keep the nucleus stuck together. And that is starting at bismuth, or elements 83 and above. The strong, or the electromagnetic repulsion is greater than the strong nuclear force. Therefore, the nucleus is unstable and blows itself apart. So all elements above 80, or all elements 83 and above, are radioactive. There's just too much positive charge in the nucleus, there's too much repulsion, and they just eventually blow themselves apart. Okay? Now when they blow themselves apart, we don't know. Okay, they're kind of like people. You know, some people are more unstable than others. You know who they are, right? There's some people you know that you're like, dude, that person is not stable. You're not sure when they're going to blow apart. You know eventually they will, Sam. You know, they're just, ah! Okay? But, you know, when they blow apart, we're not sure. But we know they're unstable. So same thing with the elements. 83 and above are unstable. They are radioactive. Eventually they blow themselves apart when it's a matter of probability, not certainty. And then for elements 82 and below, they are stable. The strong nuclear force is greater. So anything 82 and below, those elements are naturally stable. So element 82, lead. Lead is stable. Gold is stable. Silver stable. Copper stable. Carbon stable. Sodium stable. Chlorine, sulfur, phosphorus. Everything 82 and below, those elements are stable. Kind of just like humans, you can make them unstable, right? You can have a nice stable person. You could make them unstable, start messing with their minds. You know, you okay? You look ill. Feeling all right? You know, just start playing with their mind. Eventually, you'll get them unstable. With elements, you can make elements 82 and below unstable by taking away or adding too many neutrons. So you can make radioactive lead. You can make radioactive gold. You can make radioactive silver. You have to take away neutrons or add too many neutrons. Now you might think, why does adding neutrons, if neutrons act like a glue, why would adding too many neutrons cause the nucleus to be unstable? Neutrons act like a glue, but it's also, they act like a balancer. Imagine if you're driving your car and you keep adding people to your car, but they're all sitting on one side of the car. It's going to make the car sort of unstable. It's going to lean, it's going to list, okay? When you get into a car, you have people sit, all over the place. You don't have them all sit on the same side. Or a boat. You don't have everybody sit on the same side of the boat. It makes it unstable. Kind of the same thing here. If you add too many neutrons, it actually begins to make the nucleus more unstable. So it's like that sweet spot you got to hit, and usually it's a balance. 10 protons and 10 neutrons. 12 protons, 12 neutrons. So just a quick check here. Make sure you understand a little bit. Rachel, is Americium radioactive?
Yeah.
Yeah. It's above 82. What about is thorium radioactive, Colin?
Yep.
Yep. What about tungsten? Is tungsten radioactive, Rachel? No. Okay. So we are going to cover the three major types of radiation. And those are alpha, beta, and gamma. If you read in the book, they'll talk about other types of radiation like positron emission, K capture. There are other types of radiation. We're just going to focus on three major types. We'll start with the first one, the weakest one, and the least dangerous one. Well, I guess danger is relative. Alpha. And the symbol for alpha radiation is the little fishy. That's the Greek letter alpha. Now with alpha decay, you emit an alpha particle. And the word radiate means to go forth, to spread out, okay? Perfume radiates throughout the room. It spreads out throughout the room. If you have a radiant smile, it spreads throughout the room. So when we talk about radiation, we just mean these particles spread out throughout the area. So let me show you. So we've got radium. Okay. Is radium radioactive, Sarah?
Yeah.
Yeah, it's element number 88. So it's above 82, therefore radium is radioactive. okay? There are too many positive charges. And the positive charges are the pink ones. So there's just too much repulsion, too many positive charges. So if you have too many positive charges, let's get rid of some. So eventually what happens is, I like to say, the nucleus burps out 2 protons and 2 neutrons. That's called the alpha particle. So this thing comes shooting out of your nucleus, and what's left behind is 86 protons with a mass of 222. So we have radium, 88, and as Sarah said, it's radioactive. The mass is 226. You have to be provided with the mass number. So when we do these problems, the top number will be given to you. The bottom number is always 88, right? Radium is always 88. Now, when an alpha particle comes shooting out, you must conserve mass. Okay, that's a law of physics. Mass must be conserved. So if 2 protons come shooting out of your nucleus, how many protons are left? 86. So with balancing nuclear reactions, the bottom numbers have to add up, and the top numbers have to add up. So 86 plus 2 equals 88. And what number plus 4 equals 226? 222. Now, what element is element 86? So we go to our periodic table, element 86 is Rn, or radon. So what we have done is we have transmutated, that's the fancy schmancy word. We've turned radium into radon. So you can make new elements through these types of reactions. Do you have a question, Jared?
No.
Maybe let's do one more. How about we do fine, let's do polonium. Polonium 211. Is polonium radioactive? This top number can change. That's where I was saying you have to be given the top number. So I've got polonium 211. I made it up. The top number, the mass number, has to be given to you in the problem. The bottom number will always be what it is on the periodic table. So is polonium radioactive?
Yes.
Yes. Okay.
Is it always 4 and 2?
The alpha particle is always 4 and 2. So then, what's the bottom number here? 82. What is element 82? Lead. What is the top number? 207. Is lead radioactive?
No.
No. So, in the first example, we have radium. That's radioactive. It becomes radon. Is radon radioactive? Yes. So things will keep decaying. Radium becomes radon. Radon will become polonium. Polonium will become lead. And then, is lead radioactive? No. And then the radioactive decay stops. So you can start with something radioactive. Eventually, it will no longer be radioactive. Now this takes sometimes years, sometimes decades, sometimes thousands of years for this to go through this process to get to a point where it's no longer radioactive. Okay. Yep, Alex.
When you say like it could take years, is that for like each individual atom or particle?
Yeah, yeah. And again, the bigger your radioactive sample, the longer it'll take for that sample to disappear and become non-radioactive.
So could it be different for like each individual particle then?
Yes, but it's, and we'll get to the equations later, but an example would be, suppose I have 1,000 pennies, and I'm going to throw them up in the air, and every time they land heads, I'm going to remove them. Well, how long would it take until I would remove all the pennies? Okay, well, there's a certain chance that I could throw 1,000 pennies up and they'd all land heads and then we'd all be done, right?
Yeah.
Is that likely? No. The same thing here is, I mean, could this go quickly? It could. Could it take a long time? It could. But you base it on probability and say, well, what's the most likely option? Flipping 1,000 pennies and removing the heads is going to take a long time. And we'll get to those equations later where we can actually calculate the time it takes for things to disappear or decay. I shouldn't really use the word disappear because they're not really disappearing, John. They're turning into something else, okay? The polonium's gone, but in its place now you have lead.
Where does that alpha particle go?
The alpha particle is shooting through the air.
Just gone.
It goes, phew, there it went. And I will show you the radiation with a cloud chamber. That gets a little bit difficult to show, but I've got some radioactive polonium, actually, as it is. And what's it doing is it's detecting the alpha particles. You can't see them, but the alpha particle hits the metal, creates an electrical current, and makes a click. So every time an alpha particle hits it, now they only sell me a small amount of polonium because in large concentrations, if you put it in someone's food, you can kill them. So they're not going to sell me large amounts of polonium. So don't be freaking out here like, oh my God, Mr. Strauss said radioactive stuff in class. It's very, very, very out, look, I'm pointing at myself, okay? I'm not worried, right? The amount of radioactivity is extremely, extremely tiny. We'll talk more about, we're running out of time, we'll talk more about this tomorrow, but there was just recently a couple of Russian defectors who were poisoned. Or supposedly poisoned in case people in Russia are listening right now. Supposedly poisoned. Please don't get angry at me in Russia. I love Russia.